Okay, so question 4 is about a parachute, and let's try and extract the information from the question as we go. So initially at rest, so that tells us that U is 0 meters per second, and it falls vertically downwards, and then we're being asked to calculate the speed of the parachutist. So that means that we're trying to find the V, the final speed, after they've fallen through a distance of 1,300 meters. Okay, and the final piece of information is that we need to know. We can ignore the effects of air resistance. Okay, so that means that they're going to fall, with acceleration due to free fall. And if you can't remember the right number for that, okay, it's actually on the front of the paper. Look, where necessary, assume that the acceleration of free fall is g, which is 10 meters per second squared. So back down here, so that tells us how they're going to accelerate, the rate of acceleration when they jump out the helicopter. So A is 10 meters per second squared. Okay, so hopefully there's an equation jumping off the page at you. Okay, it's v squared equals u squared plus 2 times by a times by s. Okay, so we just work it through. That's 0, so that term's going to disappear, times by 2 times by 10 times by 1,300. Okay, which gets us v squared as being 26,000. Okay, we're not done yet though, alright, because that's told us v squared, okay, and we need to find v, so we need to take the square root of 26,000, okay, which gets us 161.245 blah 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 meters per second. Okay, and again we're going to look back at the question. Okay, we know that to two significant figures, so it seems to make sense to quote our answer to two significant figures, okay, which is 160 meters per second. Okay, yeah, I mean you could make the argument that you know that to 4 meters per second, I suppose, but if you did, then you still only know the acceleration to 2 meters per two significant figures. So that means that our answer should only be to two significant figures. Okay, when they're much nearer the ground, they open their parachute and this parachutist slows down. Explain this change in speed. Use ideas about forces in your answer. So you've got to talk about forces. Alright, now I think that the easiest way to do this is to draw the force diagram for what you're talking about. Okay, so look, here's our parachutist. The force downwards on them is the weight, okay, but when they open their parachute, then the air resistance force is going to be larger. Okay, just for drawing that diagram you can get 2 marks out of these 3 marks. Why? Because we've named the forces, weight and air resistance, and we've said that the air resistance force is larger than the weight. So 2 marks just for drawing that diagram. Okay. Now, with a force diagram like that, you can see that the resultant force, when we do the vector addition of these two forces, the resultant force is going to be upwards. Okay. Let's say that the weight downwards was 500 newtons and the air resistance upwards was 1,100 newtons. Okay, so that would mean that we'd have an upward force of 600 newtons, right? You do the big force minus the little force to find that out. Now, because we know that sigma F equals ma, then that means that if we've got a resultant force upwards, then that also means that we're going to get an acceleration upwards. Okay, and if you get an acceleration upwards, then that means that he's decelerating downwards. Okay, there we go. It's observed that when the parachute opens, the parachute touches ground, the GPE store and the KE store both decrease, yet energy is conserved. Well, hopefully it's fairly obvious why the GPE store decreases, because if you look at the formula for GPE, it's mg delta H. So if this number here is, this is the height above the ground, so if this number here is decreasing, then that must mean that the GPE store is also decreasing. Okay, so when the parachute was high up, it had a lot of GPE. So he's got a high GPE up here, and then down at much closer to the ground, because the delta H is now a smaller number. Okay, then that means that the GPE must also be a smaller number. It's just before the parachutist touches the ground, so and it even says when the parachute opens to just before they touch the ground. Well, in the previous part of the question, we said what was happening to the velocity, didn't we? Okay, and the velocity was decreasing. Okay, the parachutist was slowing down. So if the parachutist is slowing down, then that means that the kinetic energy is also going to decrease as well. So what's going on here? Well, the principle of conservation of energy must be true. So that means that the sum of all the initial energies must be equal to the sum of all of the final energies. And in the absence of friction, then we know that the gravitational potential energy initially is equal to the kinetic energy finally. Okay, but that relationship neglects friction. And if you open a parachute, you've got a lot of friction. So that means that we've got to put this extra term in here, which is the work done against friction by the parachute. Okay, so yes, this number is going to get smaller, and this number is also going to get smaller, but the energy is conserved. Why? Because it's all going into friction. So that means that it's the thermal store of the parachute is going to increase, and that means that you're going to get energy transfer between the parachute and the surroundings, the cold surrounding air. What else? Could we have had anything else there? Yeah, I think that those are the main points. Okay, end of that question.